All right. Good morning, everybody. Okay, so the topic of today's lecture is generic queues. So we're still talking about genericity. This time we're going to implement another data structure. It's sort of similar to a stack. So stacks and queues are both linear data structures. They're both simpler than full-blown lists, which is why you normally get taught in this sequence. So stacks, generally the easiest to implement. Queues are slightly harder, and then lists are slightly more complicated than either stacks or queues. So that's an example of a queue. It's just a, you know what a queue is. It's just a line of people in this case, right? This particular queue has a front and a back. So people get in the queue, they come out at the front, right? They come in at the back, they come out at the front. Right, so this is not like a VIP queue where people can be pulled out of the middle and serviced first. Right? So you arrive at the back, right, and you leave at the front. And everybody else stays in order throughout the queue. Right? There are other types of queues used in computing science. So there are things like priority queues where elements enter the queue with a certain priority. So the highest priority would go in the front and the lowest priority would go in the back. But we're just talking about simple queues today. So queues only classically support two operations, right? So you can enqueue, which means you get added to the back of the queue, and you can be dequeued, which means you remove from the front of the queue. Right? It's always an error to dequeue an empty queue, and that's it. So normally those are all. So those are the only two operations that a queue has to support. Normally, though, an actual queue will have other methods, right? So you can ask the queue for how many elements are in the queue, right, the size. You can ask, is the queue empty? Some queues let you look at the front element without removing it, and some queues let you look at the last element without removing it. And then you might want to implement a method like contains that checks if the queue contains a particular element. So this is what it looks like when you enqueue a queue, right? So we start out with an empty queue. I've got these pointers front and back, right? So F points to the front of the queue, B points to the back of the queue. In the empty queue, they both point to the same place, right? So if you enqueue an element, right? So we enqueue the element A, so the A enters at the back of the queue, so wherever B is pointing to. Right. That's not exactly true. So wherever this picture should really have the B over here, but we'll leave it for. I'll leave it like this for now. When you enqueue at the back. So there's only one element in the queue, so front and back both point to the same element. Right? If you enqueue another element, it enters at the back of the queue, but then B moves so that it points to the element at the back. Right? You enqueue the C, you add it to the back of the queue, and then you adjust B, right? D, and then E. Oh, E, right? So this thing B is supposed to be always pointing to the element that's at the back, and this thing F is always pointing to the element that's at the front, right? Now when you dequeue, right? So when you dequeue, the element at the front comes out, right? So the A is going to come out. And then in the slides, I think all the other elements are going to shuffle over to the left. Right, so if you dequeue, let's see what happens. Right, that's what happens. Right, and then if you dequeue again, right, so the element B is going to come out, and then the rest of the elements are going to move forward in the queue. Right, C. Right? Dequeue the C, the rest of the elements move forward. Now, if you're actually implementing a queue using an array or a list, you don't want to move the elements forward. Right? So you want to avoid moving them forward in the queue, because that means you have to copy all the remaining elements in the queue and move them up one position. Right? So when you dequeue a queue of length n, right, that takes big O of n operations. Right? So you want to avoid doing that if you can. Right. Finally, let's dequeue the D, and then we'll dequeue the E, and you end up with the empty queue. Any second now, there we go, right? All right, so those are the two operations that we need to implement. Okay, so a queue is what's called a FIFO data structure, so first in, first out. Right? So the first element that gets in line is the first element that comes out. That's opposite to a stack, right? So remember in a stack, it's last in, first out, right? So the last element into the stack is the first element that gets popped out. Right? Now it turns out queues, like stacks, are widely used in computer science and computer engineering. Right? You can imagine that a website, so websites use queues to service requests, right? So you can imagine a large website like Amazon or Google or something like that, they get literally thousands of hits per second, right? They can't process all of those web requests at the same time, right? So all the requests come in, they get lined up in a queue, and they get serviced in order. Right? That's similar with an online customer queue. So for example, if you're buying tickets at Ticketmaster or something like that, right? You know that especially for a very popular concert or some sort of event, right? It can be very difficult to get tickets for those things, right? All the people get put into a queue, right, in their order of arrival. Operating systems use queues to distribute resources. So for example, there's normally, on a home computer, there's normally only one printer, right? So if you have many people on a network, on your home network, and they all try to print something at the same time, obviously the printer can only service one request at a time, so everything gets queued up. Right? The same is true inside your computer. Right? You have a disk drive or many disk drives. You have a CPU. Right? Many processes might be trying to access the disk at the same time. Right? Many processes might be trying to access the CPU at the same time. Right? All the requests get put into a queue and they get serviced in the order that they arrive. Network devices are similar. So they use queues to determine which packets to service faster. Right? To determine which packets to service. And then there's an algorithm called breadth-first search, which is a very famous algorithm in computer science that can be implemented using a queue. And then finally, there's a whole branch of mathematics dedicated to studying queues called queuing theory. If you hit the link, you can find out a little bit more about that. All right, so we want to implement a queue. So we're talking about generics and interfaces and all sorts of other stuff in this course, right? So let's make an interface for a queue. Right? Now remember what an interface is. It's just the methods that a class must support if it implements the interface. Right? So our methods are, so Enqueue and DQ are here. Right? We've got our size and our isEmpty method up here. And it looks like we're going to do front and back as well. So we're going to return the front element and return the back element without removing either element from the queue. It's going to be a generic queue, so we can make a queue of any element type. Right? So remember, when you make it a generic interface, right, the generic type variable goes inside the less than and greater than brackets after the interface name. Right? Anywhere you need to refer to the type of element, you just use the word the letter E. Right? So we enqueue an element of type E, we dequeue an element of type E. The front and back elements, when we return them, are both elements of type E. Right? Okay, so we implement this with the list. We'll end up exactly with the queue that I just showed you in the animations. Right? So the first thing you should recognize is that a queue looks an awful lot like a stack, right? And that with the only difference being that when you take something out, it comes out at the front rather than coming out at the back. Right? So that's basically the only difference. So everything looks the same, right? You still have a list of type E, right, named Q, right? The constructor still makes an empty list, right? Size simply returns the size of the list. Enqueue is going to add the element at the back of the list, right? So that's just the add method. Right? Now dequeue is the only one that changes, right? So dequeue, we would put down here, right? So for dequeue, why are there two things here? Dequeue you remove at the back. Pop you remove at the back in a stack. Right? In dequeue you remove at the front, so you remove element 0. Right? And of course you can only remove element 0 if the queue is not empty. Right? So I've got a little private method up here that throws an exception if the queue is empty. Right? Now, here's the problem with remove. Right? So for an array-based list, when you remove from the front of the list that's in big O of n, right, which we want to avoid. Right? Ideally, we'd like a big O of 1 to remove an element at the front of the queue. So we're going to try to see if we can do that later on. Right? Front is easy, right? You just get element 0 as long as the queue is not empty. Right? Back is also easy. You just get the last element of the queue. So that's at the size of the list minus 1. Right? And toString, well, we can use the list version of toString if we like, right? And just call the list version of, and just call queues toString method. Right? So it's very easy to implement if you have an array list or list implementation lying around. But you have to remember that this is a problem. Right? So we'd like to improve the computational complexity of DQ. All right, so like the stack, right? So the next thing we did with the stack after implementing it with the list is we did it with an array. Right? So let's see what happens when you implement a queue with an array. Right? Now in the stack, it was pretty easy. So in the stack, we just kept track of where the top element of the stack was. But in a queue, operations happen at both the front and the back of the queue. So that makes things a little bit more tricky. Right? So at a minimum, we have to keep track of where the front and back elements are in the queue. Right? So we have, instead of top, we have front and back now. Right? Now you have to be careful when you define these two things, because you can define them in lots of different ways. Right? I'm going to define front to be the index of the element that's currently at the front of the queue. Right? So in an empty queue, front won't be valid, right? Because it's always supposed to be pointing at some element that's in the queue. And then back is going to be the element currently at the back of the queue. So again, in an empty queue, back's not going to be valid either. It's not necessarily valid anyway. Size is just the number of elements in the queue, right? Not the size of not the length of the array, right? It's the number of elements that's in the queue. An array, ARR, is just the array that's going to hold the elements. Okay? All right, so this is a little bit tricky. So you have to keep track of front and back. And you're going to see that keeping track of front and back is harder than it first appears. So here's my empty queue. Now notice in the pictures I had back and front both pointing at 0, right? Here I've got back pointing at -1, and you'll see, and that's what I'm going to use to implement the queue. Right? So back points, back's in front of front right now. Okay? Front points at element 0. Okay, when we enqueue an element, right, that's going to be similar to pushing an element onto the top of the stack, right? So we're going to basically use the same algorithm because you're doing the exact same thing. Right? First, you're going to check, do you have space in the array to hold the new element? Right? If not, we're going to resize the array and copy the elements back into the new array. This is a little bit complicated for a queue. Right? 2, we're going to move back 1 position to the right. Okay, so in an empty queue, I'm just going to take back and I'm going to move it to 0. Right, so I'm going to move it 1 position to the right, and then I'm going to set the element at array back to the enqueued element. Right, so move back to 0, and then set array 0 to whatever the element's going to be. Right, so that's always going to be the order of steps that we use for enqueue. Right, so if I enqueue the A, that's what the queue looks like. Right, now front points at the element 0, back points at element 0, and the A is now stored in the array. Right? If you enqueue another element, right? So I enqueue the B, right? Back moves over 1. We set the element to B, and then we're done. Right? One more. So I move back over 1, and then set the element to C. Right? Oh, there's actually a step missing here. Set the element, and then step 4, set size to equal size plus 1, right? Because we added an element to the queue. Right? And after 5 enqueue operations, you got something that looks like that. Right? So that's basically the same picture that I showed you in the animations. All right, so I think, yeah, how do we dequeue an element? Right? So to dequeue an element, I want to dequeue the element that's at the front of the queue. Right? So I'm going to take that A, I'm going to copy the A, right? Or make a reference to the A, because I want to return the A back to the caller. Then I'm going to move front over 1, right? So I'm going to make front point to the B. Actually, no. Sorry. I'm going to I'm going to make a reference to the A. Then I'm going to set that element to null to remove it from the array. I'm going to move front over 1 to the right so that it points at the B. And then I'm going to return the element. And again, there's another step missing here. I'm going to decrease the size by 1 in step 3. Right, so if we dequeue the A gets returned to the caller, front moves over 1, the size of the queue decreases by 1. Right, dequeue the B gets returned to the caller, front moves over 1, and the size of the queue gets decreased by 1. Right, when I dequeue 2 more elements, right, we're back in the situation where front and back both point at the same element. Right. Okay, now when I dequeue the last element in the queue, right, we're back in the situation where we started with, right? Where back was behind front by 1, right? So back is less than front in this empty queue, right? 1 less than front in this empty queue, right? And you might think that this is how you can check if the queue is empty, but it turns out that's not true, right? So in a few minutes, you're going to see a situation where the queue looks like this, where front and back look exactly like that, but the queue is in fact not empty. Okay, so let's enqueue one more, right? So back moves over 1, we set the element to F, increase the size by 1, right? And then I enqueue a bunch more things, right? Now notice back is at the end of the array, right? But the queue isn't full, right? There's room for 5 more elements at the front of the queue, right? So we can still enqueue more elements, right? So when you enqueue another element, right, all you do is you wrap back around to the front of the queue, right? And then set the element to the enqueued element, right? So back wraps around to the front, and notice that back is now less than front, right? So back can be less than front in a non-empty queue, right? Here, back's greater than front, right? Back here, in the empty queue, back is less than front, right? But you can have the situation where back is in fact less than front, and there's still space left in the queue. Okay, finally, if you enqueue 4 more elements, the queue is now full, right? So back is now 1 less than front, and the queue is full instead of being empty, right? So you can have back be exactly 1 less than front, and you don't know whether the queue is empty or if it's full, right? That's why we need to keep the size field around. So the size field is the field that tells us how many elements are in the queue, right? Okay, any questions so far? All right. Now, front behaves exactly the same as back, right? So I can dequeue a bunch of elements and get to the end of the array, right? But the queue still has 6 elements in it, which means I can keep on dequeuing the queue. So I can remove the P, and now front also wraps around, right? The thing to recognize in the pictures, though, is that front and back, they're always moving to the right, okay? So they always move this way in the queue, right? When they hit the end, they wrap around and come back to the front, right? But they're always moving to the right. And the other thing you should recognize by now is that front and back are both cyclic values, right? 0, 1, 2, 3, 4, 5, 15, 0, 1, 2, 3, 4, 5, 15, 0, 1, 2, 3, 4, 5, 15, right? They keep on wrapping around, right? So another way to draw this queue is as what's called a circular array, right? So this is the exact same picture as this, right? Where this is element 0 of the array, and this is element 4, right? So front is pointing to Q, right? Back is pointing to the U. When you enqueue elements, right, you just enqueue in this direction, right? So we set that value, back moves this way. We add another value, it moves this way, right? So back always moves clockwise, right? When you dequeue, Q comes out, and then front moves clockwise, right? So front and back are just these 2 pointers that are moving clockwise on this in this array. Right? And so that's another common picture of a queue, right? Of a fixed size queue, anyway. Okay, so let's go ahead and implement this thing. It's going to look a lot like a stack, right? So we have our queue class, right? It's generic. So we put in the generic type. We're going to implement the queue interface. So we write implements Q. We have our array. Right? Now remember, when we implemented the generic stack, we used an array of object to store the elements. So we're going to do the same thing here. Right? Instead of just top, we have both front and back, and also a size field. Right? So there are 4 fields. The default capacity is just the starting size of the array. Right? So in our no argument constructor, which makes an empty queue, right? We make our new array. Right? We set front to 0, we set back to -1, and we set size to 0. We can easily implement a copy constructor for this class. Right? So to implement a copy constructor, I need to copy the array. I need to copy front, back, and size. Right? So how do you copy an array? Well, the easy way is just to use arrays copy of. Right? So that'll copy the other array. And it'll copy this many elements out of the other array. Right? Front. So we set front to the front value of the other array. We set back to the back value of the other array. And we set the size to the other size of the array. Right? This copy constructor is also easy to implement. Front is easy to implement. Why did I do it this way? I should have, I should have put in another private method because we're going to be checking for isEmpty all the time. So if the queue is empty, we're going to throw an exception. That should be moved over a little bit. And then we're going to return the element at the front of the queue. Now remember, the element at the front of the queue, the array has type object, right? It's an array of object. We're supposed to return an element of type E, right? So I need to cast whatever that reference is to an element of type E. Right? So you need the cast here. Back is exactly the same, right? If the queue is empty, there's no back element. Otherwise, return the element at the back of the array. Right? Again, because the array holds is an array of object, we have to cast the element type to E. Right? For DQ, we're going to, what are we going to do? We're going to get a reference to the element at the front of the array. Right? So here, I'm not casting immediately, right? So the element actually has type object, right? Because the array is an array of object. I'm going to null out the element that was sitting at the front, right? I'm going to, now this is where I move front to the right, but remember that front is a cyclic value, right? So in other words, when it hits the last element in the array, it needs to wrap around to the front, right? So I want to move front to the right, so that's the same thing as writing this front equals this front plus 1, right? So adding 1 moves it to the right, right? Taking its remainder by the length of the array turns it into a cyclic value, right? So when you get to 15 in the array of size 16, right? When you add 1, right, that becomes 16. 16 divided by 16 has no remainder, so it becomes element 0, right? So the remainder operator turns out to be very useful in this implementation. Right? So once more, this front plus 1 moves it to the right, and then taking the remainder after dividing by the length of the array ensures that it's always between 0 and 1 minus the length of the array. Right? There's the missing step. So I have to decrease the size of the queue by 1 because we took an element out, and then finally return the element. Right? We have to cast it to E because we're returning an element of type E. Right? Okay, now resizing the array is going to be a problem because so for Enqueue, we're going to do something similar, right? So Enqueue you're adding at the back, so we're going to make sure that back is a cyclic quantity. You have to be careful though when you resize the array. Okay. So resizing the internal array when its capacity is when it reaches its capacity is slightly more complicated, right? Because front is not necessarily pointing at element 0 of the queue. Right? In other words, front can be somewhere else in the array. Right? So here's our full queue. Right? Here's an example of a full queue. Right? Front is pointing at F at element 5. Back's pointing at element 4. Right? Now, if I just resize that array and copy the elements as is into the new array, right? So in other words, I resize this so it now has size, I don't know, 32 or something like that. right, and I copy each element into the new array, I've got a problem, right? So all of the new elements are null, right? In other words, I have all this space that I've just added to the queue, but the problem is front and back are here. So when you hit the P, right, front's not going to wrap around. It's going to go to the element 16, which is null, right? So there's no element, right? So what you need to do is you need to rearrange the elements of the queue so that it looks like a circular queue again, right? There's a bunch of ways to do this, right? So I could move these 5 elements and stick them on the end, and that would work, right? And then make sure back points to the last element, right? Instead, what I'm going to do is I'm going to, when I copy these elements into the array, I'm going to start copying from the front and copy them into the beginning of the new array, right? So I'm going to copy that 5, the F into position 0. I'm going to copy the G into position 1. I'm going to copy the H into position 2, and so on, and so on, and so on, right? So in the new array, front will be pointing at element 0, right? So it really will be at the front of the queue, at the front of the array, and then back will be the last element that's in the array. Okay, so this is one way to do it, right? This is what I'm going to end up doing, right? So basically, I'm going to unwind, right? I'm going to unwrap or unwind this old array when I put it into the new array. Right? And now when I enqueue new elements, they just keep on going into the newly allocated space. Right? All right, so here's what enqueue looks like. So if the size is equal to the length of the array, that means I've hit the capacity of the current array. Right? So I need to make a new array. So my new array is called temp. Right? How big is the new array? Well, it's the old length times 2. You can multiply it by some other number here if you like. I think, yeah, so normally it's, I think most implementations use a number smaller than 2. So they use something like 1.5. Right? It has to be bigger than 1. Normally it's not bigger than 2. Right? But basically the idea is you want to increase the size of the array by some factor larger than 1. Right? And now the loop copies the elements from the old array into the new array, making sure that the front element goes into position 0. Right? So temp 0 is whatever the value of this array this front is. Right? So plus 0. Right? Now remember, front is a cyclic quantity. So whenever I use it, right, I have to make sure, or whenever I use it and I try to add or subtract something from it, I have to make sure that you take the remainder after dividing by the length of the old array. Right? Not the new array, the old array. Right? So I'm going to start at the front element of the old array, right? And I'm going to make sure that this index is always between 0 and whatever the length of the old array was, minus 1. Right? Once you're done that, I have to reassign the array to point to temp. Right? So the array is now equal to the new array. Right? Where's the front pointer now? The front now points at element 0, and back now points at the old size minus 1. Right? So once you've done all that, you can go ahead and enqueue the element. So now I can actually implement enqueue. Right? So I can set the back, I can move back 1 to the right. Right? How do I move back 1 to the right? Well, I add 1 to back. Right? And then I take the remainder after dividing by the length of the array. I can then set the back element to the newly enqueued element, right? And then I can finally increase the size by 1, and we're done. Right? So a little bit more complicated than the stack version of push. Right? It's a little bit more complicated because we have to do this copying to make sure that the queue is unwound when we put it into the new array. Right? And we have to make sure that the index that the front and back indexes are circular quantities. Okay, exercises for the student. 10:59. Well, that went a lot faster than I thought it was going to. So you should take that queue implementation, which you have. Right? So you have it in the course notes. The full implementation is there. And you should try to add that constructor there. Right? So that's a copy constructor. right? But it's a little bit different than the most copy constructors that we've seen in the course so far, right? So the copy constructor that's currently in the class, right? That thing there is another array queue object, right? Now, because it's another array queue object, in the copy constructor, you can reach into that queue object and look at its internal parts, right? So in other words, I can go in and look at this array, right? I can go and look at its size and front and back fields, right? And I can just copy all those elements over, so it's not a problem. If I just feed it another queue, right? Now you have to use the queue interface to implement the copy constructor, right? So in other words, the only methods that you can use, where does go to? Sorry, no, that's not what I wanted. The only methods that you can use are the ones that belong to the interface. Right, so now when you implement the copy constructor, these are the only methods that you can use. Right? And then once you get that working, right, go ahead and implement equals. Right? So normally, so when you implement equals the first time in this class, sorry, right? You're probably going to assume that an array queue can be equal to another array queue, right? That's not so hard to implement, right? Because what you can do is you can simply, because you can look inside the other array queue, right? You can compare the elements of the queue element by element, right? So starting at the front of this queue and starting at the front of the other queue, right? You can just compare the elements one at a time, right? So that's not so bad with if the other queue is an array queue. If it's just a plain old queue, right? So in other words, if I'm using the interface, when you try to implement that method, it becomes a little bit harder, right? Because now you have to again only use the methods from the interface, right? So in other words, you only have access to the size, Enqueue, and DQ. Right? When you do this, right, when you do either of these, actually, you want to avoid making another temporary queue or array or list if you can. Right? If you make a temporary queue or array or list, it's relatively easy. It's a little bit, it's not tricky. Once you see how to do it, it becomes obvious how you do it. Right? But to do this without creating any temporary storage, and being able to check if an array queue is equal to any other queue, whether it's an array queue or not, right, is a little bit more challenging. Okay. Any questions? Anybody? Anybody? All right. Sorry, that was a lot. Yeah, that was a lot shorter than I thought it would be. That's 46 slides. That's normally a lot more than I can cover in one lecture. But that's all we have for today.